Hello everyone, I'm Nobuo Hashimoto, a student in the Department of Computer Science in the University of Tokyo. I'm now researching image processing and hardware. I believe you all agree that image processing technology is very important in our life now. So today, I would like to explain how to accelerate an image processing filter, bilateral filter on FPGA. First of all, I would like to introduce the bilateral filter, an image processing filter. Second, I will explain our approach to accelerate the bilateral filter. There are algorithm level and hardware level contributions here. Then we'll look at the experimental results on an actual FPGA board from qualitative and quantitative perspectives. And finally, I will conclude my presentation. First, let me give you a brief explanation of the bilateral filter, which is a very popular image processing filter. The bilateral filter is well known as an edge-preserving filter. For example, please look at these two horse images. The left one is the original noised image, and the right one is the image processed by the bilateral filter. The right one doesn't seem to have much noise, and the edges, such as around the back and fur, are still distinct. I think most people will say that the right image is more appealing. Thanks to this characteristic, this filter is applied in many fields such as denoising, tone mapping, and so on. This is the overview of the bilateral filter. So next, you will understand the definition of the bilateral filter. The bilateral filter output can be obtained by the weighted sum of the neighboring pixels, and the weights are defined by two kernels, spatial and range. The spatial kernel has smaller weights if a pixel is far from the pixel of interest, and otherwise it has larger weights. The four corners, for example, have smaller weights of 1, and the up, down, left, right pixels and the pixel of interest have larger weights. Also, the range kernel has smaller weights if a pixel value is far from that of the pixel of interest. For example, the black areas have smaller weights of 0. So the overall kernel is pixel-wise product of spatial and range kernels. Neighboring pixels, in terms of both space and range, such as this, have larger weights. But on the other hand, the weight of the right-hand side is small, even though it is close to the pixel of interest, because the pixel value is greatly different from that of the pixel of interest. For these reasons, this filter has edge-preserving properties. Although this filter has wonderful properties, it has problems in computational complexity. This filter processes window size to R plus 1 times 2R plus 1 pixels per pixel, where R is the window radius. So the complexity is big over R squared per pixel, which means that if R image height or width is large, the complexity becomes heavy. Here, let's see a large-scale and high-resolution image. In order to process the same area as a low-resolution image, the window radius R should be larger, as you can see in this figure. And of course, the image height and width are large in large-scale image. So the overall complexity to process large-scale and high-resolution image is too large to process in real time, because both R, image height, and width are large. Now we have understood what a bilateral filter is. So next, we move on to the method to accelerate the bilateral filter. Our goal is to process large-scale and high-resolution images on small-scale hardware and in real time. Here we chose to use the bilateral grid, one of the acceleration methods of the bilateral filter, because the hardware resources become independent of the window radius. So we propose the enhanced bilateral grid. Also, we propose the way to implement the bilateral grid on hardware by using the pipeline method to achieve high throughput and low latency. Notice that II means that the number of clocks from the start of processing one pixel to the start of processing the next. So let's see how the bilateral grid works. Notice that now we focus on the 1D image in the x direction with the intensity values. First, when the input image comes, the pixel is discretized in the space and the range direction and projected onto the grid. This step is called grid creation. Here, the grid is 2D and the neighboring elements to one element on the grid are the pixels, which are close to the pixel and have close intensity values. So we just need a spatial kernel, not a range kernel. Next, we will blur the grid by using only a spatial kernel. This step is called Gaussian filter. Finally, we can obtain the output image by interpolating the grid by using the input coordinates and intensity values. This step is called the trilinear interpolation. These steps are the same if the input image is 2D. The difference is only that the grid will be 3D, not 2D. In the bilateral grid, the window radius on grid is variable. However, because the grid is 3D, the increase in resources is larger when the radius is larger. So we pick the radius on grid at 1 and change the radius on input. Because the time is limited, we don't explain this transformation, but this can be derived by deforming the bilateral filter definition. Here, because the filtering operation is conducted on grid, the resources do not increase greatly when the radius on the grid is fixed. So far, we looked at the bilateral grid algorithm. Next, we focus on the hardware level improvement. The overall process is the same as the original bilateral grid. But if we create grids from all input first, then blur them by Gaussian filter at once, and finally interpolate them, we cannot make the most of the FPGA performance, and we use much memory. On the other hand, grid creation and trilinear interpolation is performed per input image pixel, while the Gaussian filter is done per grid element. The difference of the number of executions and the complex data dependencies make pipelining a challenging task. Then, how we can pipeline these steps well? We solve the complex dependencies and utilize double pipeline method, macro and micro pipeline. First, we found that the areas with the same color are one group, and the data dependencies are shown as the arrows. Let's say the red and green areas are completed, for example. In order to complete the blue area, we need these green and blue areas in the grid after filtering. But this green area is completed, so we just need this blue area. And in order to get this blue area, we need 3 planes in the grid before filtering. And to get this blue area, we need R lines of input. So in summarize, if we get this R lines of input, we can get this R lines of output. Thus, we can regard the areas with the same color as one group, and we can pipeline the groups as shown in this figure. This group-wise pipeline is called a macro pipeline. We can diminish the execution time by overlapping the groups. Also, in each group, such as this blue group, we have 3 steps: grid creation, Gaussian filter, and trilinear interpolation. We can also pipeline these steps as well in this way. This stepwise pipeline is called a micro pipeline. By utilizing these two pipeline methods, we can minimize the execution time. Then, we view the memory access optimization. In the grid creation, there are read, modify, write operation, which cannot be performed in one clock. Thus, the IR equals 1 operation is basically impossible. However, we can solve this problem by utilizing the regular and the local memory access pattern. First, the blue squared area in input image is stored in a grid element with the same x and y coordinates. So the element is updated many times. Here, because input is loaded as the arrows show, the red areas comes in continuously. Now we focus on the red areas. When the first input pixel is loaded, the necessary element on the grid is loaded from memory to registers. Then the rest of the input is processed on the registers and modified at all times without storing back to memory. Here, notice that the updating values on registers can be performed in one clock. After processing the last pixel, here, the element is stored back to memory from the registers. By separating read, modify, write operations like this, we can achieve the IR equals 1 implementation. So far, we viewed this acceleration strategy. Now let's see whether it is actually faster and smaller or not. We implemented the accelerated design on the ZCU104 FPGA board by using Vivado HLS, Vivado, and Pink tools. First, we verified that the accelerated design has equivalent denoising quality to the original bilateral filter. The two images are denoised well, and we cannot tell the difference between them easily, which means that the bilateral grid shows good denoising quality. Then we compare speed and resources by changing window radius. As you can see, even though the radius is large, FPS and slices, for example, do not change greatly. Thus, we can achieve small and fast implementation in large window radius. Finally, we will compare our design with the other methods. The GPU A100 PCIe is one of the best performance GPUs, and these existing designs 2 and 3 are implemented on FPGAs. In GPU, we used OpenCV implementation in C++. As you can see, our design is the fastest of the 4 in large window radius. While ours requires more resources than 3, speed is much faster and the resources are less than 10% in a small FPGA board. Thus, we can conclude that our design outperforms existing designs in speed and resources. Now I would like to conclude my presentation. First, we shared the background information about the bilateral filter and the bilateral grid. Then, we looked at the contributions in algorithm level and hardware level. We enhanced the bilateral grid to suppress the increase in resources, and we proposed a fully pipelined implementation for the bilateral grid. Finally, we verified that our design outperforms other existing designs. Thank you for listening. If you have any questions, feel free to ask me. Thank you.